Today we are going to see some ways of constructing continuous functions. And for that we have theorem 18.2. Let x comma tau, y comma sigma and z comma mu be topological spaces. This theorem has several parts and this is part A. It involves constant functions. Let y0 be some point in the space y and you consider this function f from x into y given by this rule. F of x is y0. So no matter what your input x is, which is coming from the space x, the output is constantly y0. So it's a constant function. The claim is that this function is continuous. So let's first prove part A and then we will see the other parts. So what do we have to prove here? That this function is continuous. What does that mean? It means that if we take any open set in Y, for example here we have taken an open set V in Y, that means V is an element in the topology sigma, which is the topology on Y. Then the inverse image of V under F needs to be open in X. That means F inverse of V, now we have to show that F inverse of V belongs to the topology on X. That means it belongs to tau. Now because f is the constant function y0, it's pretty easy to figure out what f inverse of v is, like this. If y0 belongs to v, then obviously f inverse of v will be empty. Why? That is because if you take, say this, suppose this is not empty. Okay, you forcefully suppose that this is not empty even when y0 is not in v. Then there must be something in this set. Say that something is x. Now what does it mean for x to be in f inverse of v? It means f of x belongs to v, but f of x is y0. So that would force you to have y0 in v, which is not the case. So that is why if this is the case, then this will be empty. Otherwise, if y0 belongs to v, then what can you say about the inverse image? In that case, that will be the entire space x. Because no matter what point x you choose from x, f of x will be y0 which is in v, and that's why x will be in f inverse of v. And in both these cases, are we having an open set in X? Yes. Both these sets are in tau. That is why, by definition of continuity, f is continuous. Next, part B, it is about inclusion functions. Let A be a subset of X, then you can define the inclusion function j from A into X by the following rule. J basically does not do anything. You take any point from A, say small a, and apply j on it, you get A back. So that's the function. The claim, of course, here again is that j is continuous. Proof. So this time what is the range space? The range space is X. So that means you have to choose an open set in X. So V this time comes from the topology tau, which is the topology that X has. Alright. Then you have to prove that J inverse of V is open in A. But open in A means what? What is the topology on A? The topology on A is the subspace topology that A inherits from tau, which is the topology on X. And that is because A is a subset of X. So that's the natural topology. Now J inverse of V turns out to be equal to V intersection A, which by the definition of subspace topology is open in the subspace topology. That is because it's the intersection of A with an open set in X. So that's why this belongs to tau A. If you go back and see the part where we discussed subspace topology, this is the notation for the subspace topology that A inherits from the topology tau on X. So that is why J is continuous. And regarding these set theoretic identities, I leave the verification of these things to you because they are quite straightforward things. Okay. Next, part C, which is about composites of continuous functions. Say we have this time two functions, f maps x into y and g maps y into z, and both of them are continuous. Then the claim is that their composite is also continuous. Okay, so this time we have to prove that this composite is continuous, which has z as its range. So that means you have to start by choosing an open set in Z, that is, let V be an element in the topology mu on Z. Then you look at this function g, which is given to be continuous, which also has Z as its range. So G inverse of V will be open in Y, that means it will be an element in the topology on Y, which is sigma. But then this becomes an open set in Y, which is the range of F, and F is also continuous. So that's why F inverse of G inverse of V will be open in X, that is, it will belong to the topology on X term. Now it turns out that this F inverse of G inverse of V is actually the inverse image of V under G composite F. You prove these things, okay? I mean, at least you convince yourself that these identities are true. You don't have to do much. You take an element in this set and show that that element is also in this set. Don't overthink. You just go with the flow. Say X is an element here. What does that mean? It means that G composite F of X belongs to V. That is, G of F of X belongs to V, which will imply that F of X belongs to G inverse of V. So like that, these things will come. But anyway, this part I leave to you. So it turns out that this is the case. Because this belongs to tau, so this now belongs to tau. But then we have got what we wanted to get. We have been able to show that for any open set V, there in mu, G composite F inverse of V is open in X. That is why G composite F is a continuous function. Next part D, which is about restricting the domain of a function, domain of a continuous function. So let F from X into Y be a continuous function and A be a subset of the domain X. Now we are going to restrict this function F to A. So we consider this restricted function, whose definition you probably already know, but still I have written it here. So what this does is that it takes its inputs only from A. In that sense, it's restricted. But the rest is just like F. Then it just applies F itself to the input. So we end up getting again an output, a unique output in Y. But the only thing that is different in this one from this one is that the inputs come from A. Okay, so in that sense, it's a restriction of F. We have to prove that this is continuous. Note that this is not exactly trivial, although it seems like we have just simply restricted ourselves to A. But the topology on A is not exactly the topology on X. It's the subspace topology that A inherits from tau. Now, instead of proving it from scratch, which you can do if you want, but still, we are going to use the already proved parts to have this result, have this part quickly. You consider this inclusion function from A into X, which of course you know what it is. It takes any point from A and then gives that point back to you as the output. If you take any point from A as input, then that point itself is the output. That is the inclusion function from A into X. And by part B, we already know that this J is continuous. And so by part C, this composite function is continuous because it's already given that F is continuous and part B gives you that J is continuous. And finally, you note that this F composite J is nothing but the function F restricted to A. So that's how this is also continuous. Next, we have part E, which is about restricting or expanding the range of a continuous function. So let F from X to Y be a continuous function and let Z be a subspace of the range Y, which contains the image set F of X. Okay. Then we can obtain this function G from F by restricting the range. So we replace the range Y with Z. So this function actually does not change the rule of assignment of F. It only changes the range from Y into Z. And we can do this and still we won't have any problem because Z contains F of X and so the outputs are already there, okay, in Z. The claim is that this function is also continuous. Let's first prove this, and then there is a little more also here in part E itself that we will prove afterwards. In the beginning of the proof, we express what is given to us mathematically like this. I mean, using notations, because then it becomes much more clear. We are given that Z is a subspace of Y, so obviously the set Z is the subset of Y, and which also contains this f of x. Now, what does it mean for Z to be a subspace of Y? It means that the topology that we have on Z, that is mu, is the subspace topology that Z inherits as a subset of Y. The topology that Y has is sigma, so the corresponding subspace topology is sigma suffix Z. So these two things are equal. Our aim here is to prove that the function g is continuous whose range is Z. So accordingly, we will start by taking an open set in Z. So let V be an open set in Z. That means V is an element in the topology mu, which is the topology that Z has. Alright, but what does that mean? Mu is this subspace topology. So by the definition of subspace topology, V will look like this. V will be the intersection of Z with some open set in where? In Y, that is, it will come from sigma. There exists some open set U in Y, that is, U is an element of sigma, whose intersection with Z is that V. Now, our aim is to show that this inverse image G inverse of V is open in the space X. That means it belongs to the topology tau. So, let's start our calculation. We know that V is U intersection Z. So, we write that here. And then we know that inverse images behave well with all set operations. So, G inverse distributes itself over this intersection. G inverse of U intersection G inverse of Z. Now, since G is a function from X into Z, so this G inverse of Z is nothing but X. You convince yourself, okay, why these two are equal. If you cannot see this instantly, you actually do it. You take an element here, show that it's here, and then vice versa. You take an element here and show that it's here. Alright, so these two are equal. But here in place of G inverse of U, we have also written F inverse of U because they are equal. Again, because of the fact that G is functionally nothing but F. The only difference is that the ranges of these two functions are not the same, not necessarily the same. Here also, you convince yourself how these two sets are equal. I am not going to elaborate on these small things, okay? But anyway, let's accept for now that this is equal to this and this is equal to this. Alright. Now, what is F inverse of U? What type of function is F? F originally maps X into Y. And where is this U coming from? U belongs to sigma. That means basically U is a subset of Y. So, F inverse of U by definition of inverse images is a subset of X. So, this intersection is F inverse of U itself. But what is our hypothesis? That the function F is continuous. And what is U? U is an open set in the range of F, that is Y. So that's why F inverse of U will be open in X, that is, it will belong to the topology tau. So that's how G inverse of V also is in tau, which is, I mean, these two things are the same, and that's how G is also continuous. Now let's see the other half of this same part E. So this is the rest of E. So I have written like this, the rest. This time the relationship between the spaces Y and Z is the opposite of what we have done just now. That is, this time Z is the larger space in which Y is a subspace. So accordingly, the statement goes like this: if Y is a subspace of Z, then now also we are going to modify the function F by changing the range, this time by expanding the range from Y into the larger space Z, and we have given it the name H, say. Then this function H from X into Z obtained by expanding the range of F is continuous. Here again the proof is a short one, we don't have to do anything from scratch. So what you do, you consider the inclusion function from y into z, because y is a subspace of z, so we can consider the function j from y into z, and by part b we already know that j is continuous, and that is why by part c j composite f is continuous, and it's pretty easy to see that j composite f is h, so that's how h is continuous. And finally we have another part f, local formulation of continuity. I should have started the statement like this: let f from x into y be a function. I forgot to write that, but you write that yourself, okay? It's not given that f is continuous. F is just a function from x into y. That's how it starts. And then we have these things. Let U alpha be an indexed family of open sets in X, where alpha varies over this some index set J. What does this mean? Basically, it just means this, that for each alpha in J, there is an open set U alpha in X. That's what it means. Okay, nothing more than that. Such that the union of these U alphas is X itself, the space X. And additionally, it's given that if you restrict f to each U alpha, then these restrictions become some functions. All of them have y as their range, but any given one depending on alpha. For example, this one has U alpha as its domain. These restrictions are all continuous, suppose. Then the original function f is also continuous. So this is a local formulation of continuity because each U alpha is a locality. Locally, if f is continuous everywhere locally, then globally also in its entirety it is continuous. So we have to prove that the function f is continuous whose range is the space y. So we start naturally the proof by considering an open set V in Y. That means V comes from the topology sigma. Now what is it that we have to show? We have to show that f inverse of V belongs to tau. Now for each index alpha in J, this restriction f restricted to U alpha is continuous, which is a function from U alpha into Y, and this is an open set in Y. So the inverse image of this open set under that restriction will be open where? In the space U alpha, whose topology is the subspace topology that U alpha inherits from tau. Tau is the original topology on X. U alpha inherits this subspace topology. So this will belong to tau U alpha for each index alpha. But then by the definition of this subspace topology, this open set will be of this form: V alpha intersection U alpha for some open set V alpha coming from the topology tau. Alright, now our aim is to show that f inverse of V is in tau. So let's consider f inverse of V. Because it's after all a subset of X, so we can write it as this intersection f inverse of V intersection X. But recall that we are given that X is this union of all those U alphas. And then from this one, we can write this one. This is one of the distributive laws, its general version, which involves any number of sets. So what happened here is that intersection distributed itself over this union. It went inside, and we are able to take the intersection of this f inverse of V with each U alpha and then take their union. And now something about this line, you have to prove it, okay? You convince yourself that this intersection is nothing but this, the inverse image of V under this restriction of f to U alpha. All these things that I am asking you to prove are extremely straightforward. You take any element in here, it will naturally follow that it belongs to this, and vice versa. Okay, so that's how these sets are equal. But then what do you know about this? Just now we saw that this is nothing but V V alpha intersection U alpha. Now what can you say about this union? One thing that you immediately note is that all these V alphas come from tau. And what about the U alphas? They are also open in X. In the hypothesis itself, it's given that the U alphas form an index family of open sets in X. So what is this? This is an intersection involving two open sets in X. So this is open, that means this is, again, this intersection is in the topology tau. And this is an arbitrary union of such open sets, which is again open. So that's how this belongs to tau. So that's how F inverse of P belongs to tau, and this is what you wanted to show. So F is continuous. You write the last line and complete the proof.